All right, so everybody in the Zoom, if you could just do the little emoji thing with the thumbs up as well. So, okay, got it. I'm starting to see a lot of people getting there. So run that lecture 12, and I'll show you a quick command. What we're gonna do is we're gonna finish up. We're gonna design the push for the maximum heap together. And then what we are going to do after that is we are going to work through two common interview type problems that are typically used with heaps. We're also going to go over minimum heap, so it's the exact same thing, except it's the opposite. The smaller values are heapified. And then at the end of the lecture, we are going to go over what's expected from Tuesday's midterm and answer any questions you might have about the format and show you where it is you can look up the midterm study guide. Okay, so what I would like you to do is that I have this file, find kth largest here. So do the command, change directory into the source, and then copy, go up one level, go into include, and then find kth largest, and then put the period. And then after that, you should see that find kth largest is now in source. And after that, you do everything. The find kth largest is now going to be there, and it will compile and run. Yes. Oh, you don't have a question. Okay, never mind. So I'll leave that up there so everybody can do that for a moment. All right, so the first thing we're going to do is we are going to do a max heap problem together. We're going to go over the whole process. So when you're in this folder, what I would like you to do is run make prob1. And when you do that, it will give you a problem kind of similar to what we did, and we're going to work through the solution together. So I'll give everybody a couple minutes to please work on that. Okay, so who wants to tell me what the correct answer to problem 1 is? So it was a max heap problem, and yes, in the back. C. C is the correct answer. All right, so let's walk through this and see how it is that we got this solution. So what's going to happen here is now we should all be seeing this particular problem here. Everybody can see this. And what I would like to do is I'd like to show you the kind of approach that I might take if I were doing this on an exam, okay? So here, I'm going to zoom out just a little. There we go, that's going to be better. So the first thing I would do when approaching this kind of problem is I know that when I insert the first 2 elements, that the larger one will get swapped if it's the second one, right? So if this was 9 and 68 or 68 and 9, I would write the same thing here. I could just say, well, this is initially 68 and 9. I also know that 6 is less than 68, so I would draw that out here. Then I have 20. Now, 20 would normally go here, but I know that 20 is larger than 9. So I would move 9 up, and then I would just put 20 here for the time being. And I also know that 5, which is next, is going to be less than 20, so that will go here. Next thing we're going to do, we have 40. 40 would go here, but it's larger than 6, but less than 68. So I would move 6 down, heapify 40 up. And then after that, we got 64. 64 would normally go here initially and then gets heapified up. It's greater than 40. So then I would put 64 here and 40 there. And then I would put in 22. Now 22 would normally go here. It's greater than 9 and 20. So I would put 20 here, 9 here, and then bump 22 up there. And then 34 would normally go here. So then 20 is going to come down. 22 will be here. And then 34 will be here. Does that make sense so far? All right, so now what I would do is we're going to have to pop off the first 2. Oh, did you have a question in the back there? No? Okay. So now we're going to have to remove the first element. So what I would do here is I'd say, well, I'm removing the first element. In the complete binary tree representation, this last value is going to initially go to the top. I would just keep track that it's 20, but to save time, I would know that since it's a max heap, one of these top 2 values is going to come up. So 64 is greater than 34. And then 20 would go here. And then I look at these 2 and say, well, 40 is greater than 20. So I'm going to put 40 here, 6, and 20. Then I have to remove the second one. So now I have 64. And everything over here is going to be the same, except 20 is gone. And so 9 would be the value that comes up. So 9. So that comes up here. And now I would have 9 initially there. But now I don't have to write 9 out because I know I'm going to heapify it down. I have 34 and 40 are my values. So 40 is greater than 34. And then I'm here I have 9. 6 is less than 9, so I wouldn't want to heapify that up, but 20 is greater. So 20 goes here, which means 9 is swapped, and 6 goes there. And then we have these 3 here. That's 34, 22, and 5. And so then it's just the level order. So it becomes 40, 34, 20, 22, 5, 6, and 9. Does anybody have any questions about that? Yes. So the reason why we have to move here is that this is a dynamic array. So the whole goal of the design is to try to speed up the runtime of the heap and be able to search elements. We're going to see a couple of examples of that when we do our experiment. The challenge is if I have nodes, like if we do a singly linked list and doubly linked list, I have to traverse in order to find the last element. So therefore, what we're going to do with the dynamic array is we grab the element that is at the end. And I'm going to show an example of this when I go over minimum heaps in a little bit. We grab the element at the end because we can access that in big O of one time, swap it up to the top, and then we heapify it down. And that's a little faster than things we're going to see in the second half of the semester when we talk about binary search trees. So when you all are in systems programming, you've learned about maps, and we learned about unordered maps. An unordered map is a hash table. A map is what's known as a red-black tree that sorts by key value pairs. So what's going to happen is we need to be able to figure out ways with quick access. The whole goal of a heap is to improve over binary search tree, or we're going to see we can actually improve over a quick sort to get a certain element in a sorted an array. So by doing that, that's how we maintain the process. Because also when we swap up, we can just delete the last element, and that allows us to delete all the elements in the heap without compromising the integrity of the heapification. Did that address your question? All right, let me check this Slack to see if there's anything else. I see there's a typing coming up. Let me switch back to the screen here in the meantime. So that should now show, yep, we see everything there, and we see that C is correct, and that we have prob1.text if you've successfully done that. So the question in the Slack is, did we choose to start with 20 because it's bigger? So no, we choose to start with 20 if we here, because that was the same thing I was just explaining before, but I'll happily explain it again. We want to pick the element because ultimately a heap underlying is a dynamic array. So we want to get the last element, because if it's in the last element, we know that it's at the bottom. We want to maintain this complete binary tree property. So what I'm going to do is after we type, or actually, we're going to type up with the insert method, go over the delete method. Oh, 20 is bigger than 9. No, we don't choose between that. We have to choose the last element. We do not make that, we don't pick the between them. We have to choose the last element in the complete binary tree. Okay, so make prob1. All right, so what I would like to do next is I would like to, let me go back to lecture so those of you in class can see. What I would like to do next is we're going to code together a max heap. So initially we have this dynamic array, and we see that the private member is a vector of the templated type. So what we're going to do is we are going to code up push. We're going to see how that's going to work. So I'd like you to go to the include folder and go to maxheap.h, and then go to line 23. And so in this folder here, you have it as lecture 12. But if you go to include and then maxheap.h, and we go here, you see that it's going to say problem 2 starts here. And so hopefully this will clarify some of the questions in terms of what's actually going on underneath the hood. And so, Emmy, I'm happy to see that answered your question. So the first thing we are going to do is we are going to get the current location. And so, I'm sorry, the very first thing we're going to do is when it's push, we push it all the way onto the back, right? So we're just going to say heap array dot pushback and then element, like so. So we're pushing it back just like we've done before. And then what I've done is I said, well, if heap array dot size is greater than 1. And the reason I do that is because if we have just put the first element in the array, then we don't want to do anything else. It's always going to be at the top no matter what. So we start there. And then what we're going to do is we start making decisions, and we're going to use some of those equations that I mentioned last lecture. So the first thing I want to do is I want to get the current location, and that's going to be size minus 1. So we're going to say long unsigned int cur location is equal to heap array dot size minus 1. Quick question, because this is something that you'll revisit on Tuesday. Why is it that C++ data structures or memory allocation, so if we have malloc and C, and it takes in a long unsigned integer, or if I say the size, it returns a long unsigned int. Does anybody remember why it is that we want to have this long unsigned int? Yes? Absolutely right. A long unsigned int is the number that we need to use to be able to represent all the memory locations in a computing device. So for those of you in logic design, you're starting to learn about memory partitioning, and you know that we have to be able to keep track of where elements are. For those of you in computer architecture, you're learning about cache hierarchy. So we have to keep track of all these memory locations. We can't have negative memory. That is why the C++ standard and C standard have this as a long unsigned int. So we have long unsigned int, so we get the value -1. So now we're going to start applying these equations. And we learned that in order to get the parent, because this is, we're going to heapify up. If it's an even number, we will say that the parent is equal to the, we're dividing by 2 minus 1. So if it's the 6th location, 6 divided by 2 is 3. Minus 1 becomes 2. So that's for even. So we're now going to say that if cur location mod 2 is equal to 0, we're going to say that parent, let me run through, let's see, int current location. So I'm going to apologize to you. Int current location, well, actually, no, that's fine. We can leave that there. We're going to say long unsigned int parent. And we're just not going to define it for now. And we're going to say the parent is going to be equal to current location divided by 2 minus 1. And now the reason why this will compile, even though I haven't defined it, is because I'll say else. And what the compiler knows is that if I define parent in both the if statement and the else statement, then I will be able to guarantee that parent is defined. So if you get that one that said goes through, doesn't define anything, and it looks like you define it in several case statements, check to make sure it's in every possible case. So here, what I'll say is parent is equal to current location divided by 2. So if it's at 5, 5 divided by 2, putting into a long unsigned integer will give us 2. Okay, so does anybody have any questions about this before we continue? All right, so the next thing we're going to do is after we have the current location and we have its parent. So now we're going to say if the location at current location is greater than the value at the parent. So we're going to say if heap array dot at cur location is greater than heap array dot at parent. So what we're doing is we're doing that process of heapifying up. And that allows us to be able to determine and keep going how we're going to find everything. Oh, you know what? I realize why I have to do that. Okay, so I owe you an apology. Please move this current line at line 28 above the if statement. And I'm going to explain why in a moment. As I was about to give you guys a seg fault. All right, so let me leave this here so everybody can make that error. Dr. Morrison's, you can fix Dr. Morrison's error. Is at 28, and now it's at line 26. So what's going to happen is we're going to have an initial current value, and then parent, eventually we're going to update it, so parent is going to be equal to cur. And so we're going to keep doing this while loop until we hit equal to 0. So the other thing, and I apologize for this as well, what we're going to say is we're going to say while true. I'm having a morning. All right, so let me read through this through everything again. So what we're doing here is we have the heap array size, and we are getting that location, and we're going to keep iterating until we break the while loop. And I'm going to give you a couple of break conditions. So here, I'm going to zoom in so you can see again. Long unsigned int cur is going to be initially the end of the array. And then while true I'm going to say if the heap array size is equal to 1, greater than or equal to 1, then what we're going to do is we're going to get the parent, and then we are going to determine where that it is based on the location. Then I'm going to say, well, if it's greater than here, what I'm going to do is I'm going to say, all right, we're going to perform a swap. So just like you're doing in coding challenge 5, you get the temp is equal to heap array dot at parent. And then we're going to say heap array dot at parent equal to the current location. And then we're going to set the current locations equal to temp. And now the last thing we're going to say is, if we performed a swap, we're going to set cur location equal to parent. So now we're going to come up with our break statements. Our first break statement is that if this doesn't qualify, we're just going to break. So let me put this here for now, else break. So what that means is, if I'm heapifying and I find a value that's larger, that's above me, we stop and we break the while loop. The next place I want to break is I'm going to say if cur location, so this is now, it's been updated, we found the parent, and this scenario says if the current location has been updated to 0, now we're going to break as well. And so I'll go over this one last time, but line 51, we need this because we need to know the new current location. Because we're going to keep moving up the heap until we find our value. So Simran, did that address your question? Good. So our last one that we're going to put in a break statement here is after line 6, what I have is line 60, and if it's greater than 1, else break. Okay. And so let me explain the whole thing again, just to make sure that we're clear on what's going on and how we're using a dynamic array to do this heapification. By using the math, we're going to iterate through until one of three things happens. One, we realize that we only have one element and we're going to break. The second one, so that's the last thing we just coded. The second one is if when we calculate the parent is greater than the current value, that means I don't want to move it up anymore. We want to stop. That's our second break statement, and that's the break statement that's here at lines 50. What I have is lines 54 and 55. The last thing is if we heapify and we actually have the largest possible value. We have heapified all the way to the top of the max heap. That's where I say, well, if current location is equal to 0, what that means is I have found the beginning of the dynamic array, which is also the top of the maximum heap. Does that make sense? All right, would anybody like me to show any other portion of the code again, just so you can get what you need in there? Yes. I can, sure. Where do you want me to zoom out to? Okay, so the while loop is just while true. And then first condition is heap array size is greater than 1. And then inside, I'll say, get the first parent, and we're going to keep going. We have it mod 2 is equal to 0. That's where I use the parent is mod 2 -1. So just to review, if I have these nodes, right? So I have 0, 1, 2, 3, and 4 if we're doing it with a dynamic array. So with 4 divided by 2 is equal to 2, which would actually point here, and that's not what we want. So therefore, I say -1, and that gets me that one. Same thing with 3. 3 divided by 2, when I put it in a long unsigned integer, is 1. So we see that it's pointing to the correct parent. All right, so let me update it and run it. And we'll go back and we'll make sure that we'll see if I made any other mistakes. And so in SRC, there's a folder called test max heap. And so I'm going to run make test max heap. And I'm going to show you the output and what we expect to see. So what's actually going on, you're going to see that I have pushing. And at each stage, it's going to have the current state of the maximum heap. I have a friend operator that prints out all the elements in the array. The reason I've provided this is so that way, if you are studying for your test and you want to come up with your own problems, you can come up with your own array, plug it in, and then be able to see the whole process for the answer. And then it prints out the array after I do every pop, and I'm going to go over the pop code in a bit. The thing I want you to see is that when you pop all the elements off, excuse me, I'm sorry, 81, 44, 33, 27, 21, 7, 1, and 0. We are able to get what is known as heap sort. So I have the maximum value down to the minimum value. So we are able to do that in big O of n log n time. And what we're going to learn is that we can actually use this to beat quicksort. And then I do the same thing. I test my templates to make sure it works. And then I put in a bunch of characters like so, and then pushes and pops. I'll show you pop in a moment, but when you run that, you should see prob2.text to indicate that you've completed the second of the 3 problems we're going to do today. Does anybody have any questions on the push aspect of max heap? Let me check the Slack too. I don't see anything there. So now what I would like to do is I'm going to bring the code back up, and I'm going to show you some of the other methods. I have a top method that just gets the top element in the heap, and the way that I do this, and I'm going to zoom back in so that way everybody in the back can see, is just get the front element of the dynamic array. If I want to get the size, I just get the size of the dynamic array, so now we're aggregating. If it's empty, I can just use the empty method from the C++ library. With pop, if it's empty, we're going to do nothing. So that's the very first step. And so now we're going to use those other equations to determine whether or not we actually want to do anything. If there's one element, then I'm just going to make the vector empty. So now we just clear it out. Otherwise, if there's 2 or more, now we have to run our algorithm. So what I like to do is I'm going to scroll down to the beginning. And so if you remember, what we're going to do is we're going to move the element that's at the back of the array. So there are a couple questions about this. And I want to make sure this line of code will address both of these questions. We take the element from the back. When I went through the example, I said, all right, I'm going to take the element that's at the very end. It's not going to be the smallest, and that's a drawback of max heap. It's not guaranteed to be the smallest. It's just the element that sits in the end of the complete binary tree. And we move that to the front. Then we delete the element off the back. So now the value that was initially at the top has officially been removed. We've overwritten it, and now we've deleted, so that way we know how the size of the array is. Then we're going to do the exact opposite process. We're going to have a current location, but I'm going to start at the root. That's going to be 0. So instead of starting at the end, I'm starting at the beginning. The next thing I'm going to do is I'm now going to use the equations that I presented last lecture to determine where the left and right child are. So if I'm starting at 0, it's going to be 2 times 0 plus 1, so that's the left. I'm going to point right because it's your left. Your left is 1, your right is 2. and then it'll keep going. So we're going to heapify down. So what happens if I only have two elements? So let's say I have 30, wow, that's big. Let's say I have 38 and 27. So I don't have a second element. The size is 2. So if I have both children, I will know this is the case because the value of right child will be less than the heap size. So if I have 38, 27, and 29, the size is 3, and so heap size will be 3, and right child will be 2. Does everybody see that? So if right child is less than, I know for a fact that I have both children. And because we've been putting it in a certain way, it's a complete binary tree. And when we get into binary search trees, we're going to see that that's a thing we have to seriously consider. So what I need to do is I'm going to see if either of these are less than the value, the value that's at the current location is less than the left child or less than the right child. That means I want to heapify down. And we saw an example where one was bigger but the other was smaller at the very end of our example. So what I do here is I do a swap location. I'm going to zoom all the way out so you can see this whole line of code. And what's going on here is that I'd set my swap location, I compare the left and the right child, and whichever one is less, that's the one that I'm going to say you should swap with. I'm sorry, whichever one is greater. And the reason why is if I have 20, let's say I have 64 and 37, right? I know that I want to put 64 up here because if I pick the bigger one, then every value down here is going to be guaranteed to be less than 64, but every value down here is also guaranteed to be less than 64. So that's why we choose that. So that's what's going on here. And once I get that swap location, then we do the same thing that we just did. Then we, just like before, we set current location equal to the swap. And if we violate that condition, we are going to break. Does that make sense to everybody so far? The next thing I want to show you is what happens when I only have, so if that condition isn't met, then the next thing I want to check to see is if left child. So if I have only one left child and I don't have a right child, this condition will meet in the else if case. Because before I had both, but if that gets violated, that means right child was less. Right child met that condition. I could potentially have a left child, but I could potentially not have a left child. So in the left child, it's very similar code, except I don't have to do this swap and comparison. All I have to do is say, if the value at the current location is less than the left child's value, therefore, to swap those and update current location to the left child. And if that isn't true, again, we break. Finally, this else case here, what's going on there is I've checked to see if I have a valid left child, valid right child. Your right, my left, sorry. So I check to see if I have a valid right child. It's not there. Then I check to see if I have a valid left child. It's not there. Therefore, I do not have a valid child at all. That means I've reached the bottom of the tree. We end the while loop. Does that make sense? The next thing I want to talk to you about is minimum heaps. So with a maximum heap, I am guaranteed to have the largest possible value, and I can do heap sort if I want to do from max to min. For a minimum heap, it's the exact opposite. We're going to go from min to max. So the code is very similar, except there's going to be a couple of differences of greater than or less than. So what I'm going to do is I'm going to walk through an example, and then I'm going to ask you to do problem 3. So in this problem, I have an array representation, and I'm going to find the last of the final min heap following these insertions and removals. So we have these insertions, and then we remove the top 2 elements. So with 41, 41 is by itself, so we just put that in there. Then what we're going to do is 7 goes in there, and it goes in that location. Since it's a min heap, 7 is less than 41, so we're going to flip those. Does everybody see that so far? So maximum heap, we are left alone. Min heap, we flip. Then we're going to put in 11. That should be 12. Okay, I missed 11. All right, pretend 11 is not in that problem. All right. Now we're going to put in 26. 26 is greater than 7, so we do not heapify. 65 is greater than 41, so we leave it alone. 53 is greater than 41, so we leave it alone again. 83 is greater than 26, so we leave it alone. 10 is less than 26. So that is where we get our complete tree, and then we're going to swap. We use those equations to determine where the parent is, and then we swap 26 and 10. I would do the same comparison. 7 is less than 10. Therefore, we terminate that heapification. And then the last thing I put in is 21. 21 is less than 65, so those are going to swap. And then 21 is less than 41, so it will swap again. Does that make sense to everybody so far? So now we're going to do the same thing. We're going to remove the top 2 elements. So what's going to happen is, just like before, we're going to grab the last element in the complete tree, which is the last element in the dynamic array. And then, so 65 is going to become over here. And so now we're going to heapify down. The rule is the exact opposite. For a max heap, we pick the bigger one and move it up. For the min heap, we pick the smaller one and move it up. So we're going to swap 10 and 65. Like so. And I missed 11 in the animation. I apologize, Emmy. So now what we're going to do is we're going to update that cur location. So when I updated that cur location, that allows me to calculate the next pair of children. So now we see that I've got 65, 83, and 26. 26 is the smaller of the two, so I'm going to swap 26 and 65. Then I go to the end, like so. So now the last thing I'm going to do is I'm going to do that second removal. So 65 is going to come up here because that's the last value. And then I'm going to delete the last element off the vector. And so now I'm going to heapify that down. I pick the smaller value of 21 and 26, and then I swap. And then 65 is we update that child value. 65 has 2 smaller values, 41 and 53. 41 is the smaller of the two, so 65 will be swapped with 41. And then we've reached the bottom. All right, does anybody have any questions besides how I screwed up my animation? So I'm sorry about that. So what I'd like you to do is, next I want you to run make problem 3. Oh, make problem 3. And now it's going to be a min heap problem. It's going to do the exact same thing, except now we're going to run the min heap instead of the maximum heap. And I want you to select the correct solution. So please take a couple of minutes to work on that. So would anyone like to share the correct answer? Yes. A is the correct answer. We see that if you press A, it's going to come out, and you'll see you have prob1, prob2, and prob3 there. And if you run test.sh, provided everything's working, so you will get 110 out of 110. And so you have until midnight, of course, to make any changes, review the video, ask questions of me, ask questions on the Slack to obtain the full credit. All right, so what I want to do is I'm going to go back over and I am going to work through the problem to show you how it is that I got this answer. So this should now pop up there. And there it is. All right, so here we have a min heap. So a minimum heap, on a problem like this, if you look at the first three, you can get a general idea of what the, you should be able to tell exactly what the answer is going to be. And this will save you a little bit of time if you're trying to work it out. So 68 will initially be at the front. 68 and 9 are going to be, 9 would heapify over 68. And then 6 is going to be less than 9. So the way this would actually work is I know that this is going to be 6, 68, and 9. Does that make sense? So that's because 9 gets heaped up and then 9 gets heaped down. So 20 is going to be less than 68. So 68 is going to be moved down and 20 will be here. 5 will be moved here, but then 20 gets down and then 6 is going to be moved here and then 5 gets moved up. So this will be 6 and this will be 5. Now we're at 40. 40 is greater than 9, so that stays put. 64 is also greater than 9, so it stays put. 22 would go here. It's less than 68, but greater than 6, so 22 stays there. And then 34 is less than 22. So that's the initial, if I'm just doing the insertions, that's the final min heap. Does that make sense to everybody? So now what I'm going to do is I'm going to go through the process of popping 2 elements off. So the first one is going to be 5. Which value is going to go to the top? Can somebody tell me which value they think is going to pop up to the top? Let me bring up the Slack so that way people can answer too. Which value, what's going to be the value? Yes, 34, absolutely right. We grabbed the element off the back and I see that there's 3 answers of the exact same thing. I bet Parker is also typing 34. All of you are correct. Great job. So 34 goes here. And so now when I do this, when I'm working on problems like this, I realize that if I start doing a little too much more, I'm now going to erase and I'm going to lose credit and everything's going to be, not lose credit, but I'm going to lose track of what's what. So now I would start saying, well, 6 is less than 9. So 34 is going to go here. So now I see 22 and 20. 20 is the smaller one, so 20 is going to go here, which means 34 will go there. It has no children, so this becomes 22 and 68. And everything over here remains the same. All right, just to ask again, I want to see the participation. What's the new, I'm going to pop one more element off. What's going to be the value at the top? Yes, 68, absolutely right. And Sebastian and Selena have also, and Corrine have also answered 68, so very good. So 68 comes here, that goes away. 9 is less than, so 9 is going to move up here. 68 is going to go here. We see that 40 and 64. And so 40 pops here, and 68 goes there. And so then you go through and you do the level, what is known as a level, we'll learn this a lot more detail, called a level order traversal. So it becomes 9, 20, 40, 9, 20, 40, 22, 34, 68, and 64. All right, does anybody have any questions about how I derived that? All right, so first question, why did 9 heapify then switch to the right-hand side? So what's going to happen here is when I start out, I do 68, and then 68 goes to 9, right? But then 9 is less than 68, so then 9 goes here and 68 comes down. Then I put in 6. 6 comes here. 6 is less than 9. 6, 9, and 68. So when you have enough practice and you're trying to save yourself some time, let me get off of this and go back to the normal thing here. Stop video, class cam. All right, so getting back to this, what the piece of advice I was trying to give you there is that if you're trying to find little shortcuts that when you have knowledge, and you're trying to figure out time to save yourself, you have an exam, you want to optimize your test taking, that's one trick that I developed when I was a student. I was like, okay, I know the first three, boom, 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 knock it right off. Instead of worrying about having to rewrite everything, that would save me 25 seconds. And once you practice enough and get the hang of certain things, you save yourself 25 seconds here, you save yourself 35 seconds here, you add up enough problems, and then suddenly you've saved yourself 20 minutes. That gives you enough time to check things over. And so that's why I was presenting it that way, just to kind of give you one way that I developed in order to be able to work on that kind of problem and reduce the time complexity on the exam. So for the first student, forgive me, let me bring the Slack back up here. Natalie, did that address your question? Okay, so Carlo looks like he has the same question. What would happen if you stopped 68 and 20 and then 28 and 9? So let me go back to sharing this. So William, I want to make sure I'm understanding your question correctly. So your question, so now we're back here. So the question is stated, what would happen if you stopped 68 and 20 and then 20 and 9? So if are you talking about here, right? So if I put in 20, we now move 20 up. So now 20 comes here and 68 comes here. The crucial thing with a maximum heap, we don't want to maintain the order. We don't have to maintain a sorted order. We just have to get the actual, get everything down. So if we have these values, which if 68's here, right, and 64 is smaller, sorry, did I screw that up? 64 is smaller, so I should pick the smaller value. But this was 40, so 68 was simplifying down to 40. So we don't want, the key thing you got to bear in mind with heaps is that the result is not fully sorted, and that's a benefit. And I'm going to show you this in the 2 interview questions. We need to pick the values that ensure that we want the smallest values in the min heap to bubble up. It's not necessarily sorted. So the confusion tends to come from, I got to sort it, I have to sort it. Not necessarily. You just have to make sure that you perform the correct swaps. Okay, so you're welcome. And the last question, why did 22 not switch positions? So when we do 22, what's going to happen is 22 is going to be put here. That maintains the complete binary tree. 22 in a minimum heap is greater than 20. The only guarantee that I know in a minimum heap is that all the values from here down are greater than 20. So this is a valid minimum heap. And when I'm going to show you in the find kth smallest problem, that I put it in the wrong folder, what you're going to see is that all you need to do is perform this heapification. And when you do that, that will allow you to get this solution faster. All right, so Natalie, did that address your question? Right, so I'll wait for that. Let me bring back the presentation. Okay, and then we're going to go back there. All right, so when you're doing job interviews, so many of you are starting to look for internships, considering looking for internships, maybe you're going on LeetCode, trying to figure out how it is that you can put yourself in the best position to succeed for when you're getting a job, because that's why you're here, right? You're not just here to hear my wisdom. You're here because you want to get paid. When an interviewer is asking about K, they say find the kth largest or sort K doubly linked lists. What they're doing is they're leading you towards using a max heap, but you have to understand why. We're going to cover a little bit of why it is that we call this K for a heap, And it's going to be covered in much more detail in the algorithms course. So here is the type of problem. You want to find the k largest element in an unsorted array. And typically, in this type of question, it will follow up that it wants you to beat big O of n log n time. And so a lot of students will start going like, well, maybe I should use a hash table, but if I hash, the unordered map isn't sorted. If I use a tree, that gives me big O of n log n. What do I do? So the crucial part is the kth. So let's walk through and see what happens. So I can say that the heap sort, if I want to find the kth largest element, will be found in big O of n log of k. But Dr. Morrison, you told me that what's the worst case scenario? Big O n log n, that's the whole point. You're right. It is the worst case scenario. But the k is what allows us to fix that worst case scenario. So let's think about an array of some sort of size. If I have an array of 2 elements, I don't have a 4th largest element. I have 1 or 2. When I have an array of 4, I have 4 largest elements, right? If I have 5, there are always going to be some sort of 4 largest elements. If I have 10, there's going to be 4 largest elements. If I got 20, there's going to be 4 largest elements. So the crucial thing is, what happens when I know that an element is no longer one of my 4 largest elements? That means I can add smaller values and larger values until the end of time, and that value will never be in the top 4. So why bother saving it? I don't have to heapify the entire array. I only need to heapify 4 of them. And that's how I'm able to beat big O of n log n and get this big O of log k, where k is going to be a constant based on how many elements you have in a maximum heap. And this is beneficial because all we need to know is what the largest value is by looking at the top. That's big O of 1. So what I'm going to do is I'm going to say, well, if I have a largest value, I can heapify, I can remove the top of the element, and that'll be that. I'll still have the top 4. So I'm actually going to use a min heap. I do a min heap, give me the top 4 elements, and I will be able to solve the problem. So let's walk through this step by step and see how it is that I'd solve this. And so by going through it step by step, we're actually using a dynamic programming approach. To remind you that you will need to identify the definition of dynamic programming sometime, maybe next Tuesday. If I know the first 5, and I only need to replace 1, then I don't have to recalculate every single time. So that makes quick sort slower if we had to do that. By using the heap, we gain that benefit. So let me walk through the animation. So I've described this about 5, 17, and 38. They'll have 4 elements. So here are the first 6 elements that I'm going to run here. So I got 22, 17, 44, 9, 55, and 18. The first 4, 9th is the 4th smallest element. If I add another one, 17 becomes the 4th smallest element. I mean, it becomes the 4th largest element, 55, 44, 22, and 17. So I never need 9 again. Let's get rid of it. I'm done. If I put in 65 and 8, it's still not going to qualify. Same thing, I put in another element. If I were to sort those, we see that it's 55, 44, 22, and 18. I don't need 17 anymore. So if you walk through this whole process of 10 elements, we're going to see that no matter what I do, I have 4 values in there. So I only need to sort 4, big O log n log k. So if you see k in a problem, think max heap, min heap. So what I'm going to do, I'm going to show you the solution, is I've created a minimum heap. And once we have k elements, the kth smallest element is going to be at the top. And so if I find a larger value, I pop and then heap. And then the smallest value that's there will heapify. That will now be the kth smallest element. So then I've described this whole thing about big O of n log k versus log n. we now see that we can use the heap property and that we only need the top element there to reduce the complexity. Right? So I see there's a question being typed in the Slack, and the question is, wait, do we need the largest elements or the smallest elements? At the start, you need all four. And I'm going to walk through and show you what's going on here. So what's going to happen is I'm going to have 22, 4, 44, 1, and -3, 33. And so when I heapify these four elements, -33 is going to be at the top, so I can say that that would be the fourth largest element. Then if I put in 405, the fourth largest element won't be 33, it'll be 1. So I would pop the element off of the top of that min heap and then put it in there. So now the element at the top of the min heap will be 1. If it's 0, I'm not going to put it in there because 0 would be less than 1, and therefore the fourth smallest element in the heap is still going to be 1. If it's greater, if it's like 99, I would remove 1. 22 gets heapified to the top, and that is our new correct answer. So K, in this case, K is 4. So that's what I mean. If I'm going through and I have 1,000,000 elements in the array, but I only need to get the fourth largest element, I would only want to store 4 elements in the heap. So let me walk through the code, and hopefully this will clarify some of the questions. Do we use a min heap because the lowest value is at the top? Yes. Also, are we assuming K can't be equal to N? K is, worst case would be equal to N, but the whole idea is that you should be able to demonstrate that a maximum heap in this kind of problem for this kind of data structure will beat big O of N, big O of quicksort for every case except if I'm trying to find the very largest value. In that case, it will be a tie. So please let me know if that has addressed both of your questions. So in this code, the find kth largest, I'll quickly show this to you. Let me go up to SRC. So I'll just do cd src, and we'll do vim find kth largest. And what's going on here is I've done this, but I've also done it in a way to kind of reinforce other concepts that you might see on Tuesday's exam. So that's still not going. Oh, yay, it worked. Okay, so find kth largest. Let's first go to main. And in main, I've created a void pointer of unsorted, and I've malloc with the 12 times the size of int. So I have an array of 12. And then recall that I have to cast to add context to the void pointer, and then I dereference using the star. So you can see I'm doing all of this to create this array. And then for pre-sorted, I print all the values out, again, adding context using int star, dereferencing. Nowadays, you've learned enough, you have enough understanding, you know what's going on underneath the hood. You could use standard vector to do the same type of concept. Then I create the min heap, and then I go through all 12 possible solutions. And so here what I'm doing is I'm creating the min heap for kth. If kth is greater than the length, I'm going to say that that's invalid. So if I put in 13, it wouldn't work. Then what I'm going to do is I'm going to iterate through the first kth. So in the example that Nikita and I were just talking about, if I have 4, it'll put in 4 automatically. And I have this comment here just to say I'm doing that again to reinforce previous concepts. You could use a standard vector if you so choose. And then here what I would do is it's a min. So I would check to see if that value is greater than the top of the minimum heap. Then I would pop that off the top, and then I would push the value onto the heap, and that would give me the correct answer. And then I would print out the correct result. Or does anybody have any questions about my approach to this? Okay, so the next thing I want to do is I want to show you another thing where we can use maximum and minimum heaps to be able to get real-time fast answers to a find median question. Okay, so there's everything, and then there's the run. Another question that you might run into is median is the middle of an ordered integer list. So I could do that. Or if it was a double, let's say I want to figure out what the median score is on your exam next week. Split it in half. The student at the middle is going to be the median. That means if the median was an 85, that means half of the class got better than an 85. If it's an even number, I have to take the two middle, add them together, and divide by 2. And so the question here is, so the median is the middle two values. So I showed the examples. Design a program that supports the two operations. Add an integer from the data stream to the data structure and return the median of all the elements so far. So the data stream is the crucial part. If I read in one element, I know what the median is. If I read in 2 elements, I can figure that out. If I have a third, in a worst case scenario, I would need to sort and then do that. Fourth, I need to sort and do that. And you can see that as the value gets bigger and bigger from the data stream, that it becomes more and more complicated. So we have to come up with a better way to do this. And this is where we can apply our knowledge of max heaps. So there's the brute force that I just described. Quick sort also doesn't work. So what we do know is that median splits in half. So what I can do is I can say, well, I need the largest value on the left and your left, largest value on the left, smallest value on the right. And that's all I need to solve the problem, right? As long as they are even size. So what I would do is I'd say initially put on the left. If one is greater than the right, I would put it on the right. So in this case, I don't need to sort the whole thing. I can just heapify and beat the quick sort. So I can use the maximum heap on the left and the minimum heap on the right. And that will get me the correct answer. So I will walk through this whole thing. I would heapify, and what you're going to see in this animation is the dynamic array ordering. And so what will happen is, if it's 7, I would say, all right, 7's less than 10. So what I'm going to do is I'm going to move 10 over to the right, and then 10 plus 7 divided by 2 becomes the new median. So I would put in 6. I would heapify 6, so 6 is going to go here. And then the new median is just 6, because 6 is in the middle. I'm sorry, 7's in the middle. So we have a max of 7. Then I put in 5. I'm going to see that I have one more, and that 5 is less than 7, so I'm going to move 7 over. 6 plus 7 is now onto the maximum heap, so that becomes 6.5. And we can go through this whole process to move everything over. And so we can use our maximum and minimum heaps to solve this problem. So this slide here is just the pattern that I described, and forgive me, we have 10 minutes left. I want to make sure I describe the exam. But this allows us to use the maximum heap. So let me run find median. And now I have a data stream just like the problem states. And I can say 9, median's 9. I can say 15, and median is 12. I can say 22, and we see that the pattern is being followed, and I can find this in a faster time than I would do if I needed to quick sort everything. So I could do 101, 77, 99, 88, 96, so I'll just do 97, and so on. I can do 1, and then I'll terminate with a -1. So that allows me to be able to run that algorithm faster than I would do if I needed to do quick sort. Does anybody have any questions about my approach to that problem? And so that's going to be available. You're more than welcome to review that to try to get through LEAP code and then practice for job interviews. Oh, okay, never mind, you don't have a question. All right, so on that note, get through blah, blah, blah. All right, so midterm exam. First, there is a link that may also be found under lecture 13. So Tuesday will be lecture 13. And what I have on this page is the description of the exam. I have how the exam will be given. So crucial thing, first exam, it's going to be on Sakai and it have to be here. Unless you are in, the only way I will grade a waiver is that you have to be either in Q or I, or you have to have a waiver from Sarah B. If you have a waiver from Sarah B, I already know about it. So just make sure you reach out and coordinate that. So the Sakai has an IP lock. So if you're not here, you won't be able to take it. So if those of you who, there's about 45 of you some odd who regularly attend on Zoom, and if you have to walk clear across campus, I don't blame you for not wanting to make that walk. But on Tuesday, you're gonna have to. I expect everybody to be here. So we'll be on Sakai, and it'll be multiple choice, just like the coding challenge problems and just like the problems that we've worked on in here. So it's going to be made available. It's going to be March 23rd, and we'll close out like so. So let me quickly bring up the next part. So it's going to be closed books, closed notes. Can't ask for any, Hagrid, or can't ask for any Hogwarts owls, work on anything like that. You have to do it on your own. Right? I will provide scrap paper. Several TAs will be here. We'll make sure that everything's covered. I was initially going to print a copy of the exam, but I realized with the matching, what ends up happening is Sakai automatically sorts it, and I realized that was going to cause way more confusion than printing out a copy for everybody to have might provide a benefit. So I've changed my mind on that. So, but we will provide scrap paper for you. You don't have to, you're not permitted to use a calculator, but I've made the problems like doing a amortized analysis or figuring out what hash you should use with mod 7 that is reasonable. It can be done quickly without a calculator. So here's what we have covered so far. So everything in red is what we've covered. And so we've covered imperative, object-oriented programming and data structures, modularity, specification, data abstraction, classes and objects, and genericity. We haven't covered inheritance or polymorphism yet. We've covered lists, stacks, and queues. We've done sorting algorithms, and we've covered priority queues. And for the other part, this is all from the course description, we've done all the rest of these parts. We've covered demonstration and understanding and proficiency of C++, object-oriented programming, data hiding, so abstraction, encapsulation, templates and design patterns, so you've done a lot of that in your coding challenges. You've been able to analyze the performance of data structures, so we know big O of n, we know amortized analysis, as to select the right one for each situation. And then we have apply and use data structures for real-world application, employing abstractions to make them work together cleanly and safely. So you demonstrated that most recently when you were working on building your own priority queue. So there are going to be several types of problems. You should be able to identify these terms. So now you're familiar with all of these different data structures. And you had a problem very similar on Coding Challenge 5. And you should be able to identify real-world application where you'd use them. And you had a problem very similar on Coding Challenge 5 as well. You should be able to identify several terms: encapsulation, abstraction, inheritance, polymorphism, data heap, instruction stack, registers, pass by value, call by value, or is it call by reference and pass by value. You should be able to tell me what recursion, memoization, and dynamic programming are. You should be able to identify some of the code that we did early in the semester. You have some void pointers. Tell me what the output should be based on your knowledge of the size of the data structure of the primitive types. Be able to iterate and then identify what the output should be for a specific class. So you should be able to do a problem with a recursive trace. I've gotten a couple questions about this. My recommendation is to make your own types of problems where you have a recursive trace and see if you can figure it out. So if you can do that, then you'll definitely do well on my exam. Same thing with void pointer and memory allocation. You should be able to correlate that with a corresponding member initialization list. Given a fundamental class, select the corresponding output. You've done several problems, including you should be able to say, well, what's the address of the this pointer? And then given a class, you should be able to tell me which ones are const and which ones are not const. Forgive me for neglecting the question. I still have 3 minutes. I want to make sure I get through all these slides. That big question. In the following code segment, a new programmer has attempted to aggregate templated classes. They've encountered several compiler issues. You've worked on several problems like that. Practice those, you should do fine. Select a correct overloaded operator given a template. Select a correct friend operator given a template. You should be able to do initial partition for quick sort as presented in Coding Challenge 5. You should be identified the final state for a max heap, a min heap, and a linear probe hash. And I can also expect you, given some code to state the expected output, and you should be able to do a linear probe. So first, let me address the question. I have one last thing I want to show you. We'll be tested on makefiles. You will not be tested on makefiles. So lab 6. Lab 6 is next week. I'm going to switch the submission for that week only. And the reason why is because there's students who have lab on Monday. There's students who have lab on Tuesday. I figure it's unfair to the students who have lab on Monday to hold those. So basically, as long as you go through and push it to GitHub by Wednesday, your grading TA will just look it over, and that's how you can do the submission. So I want to make sure there's fairness. And so instead, I will hold office hours during the normal lab on Monday. All right, so midterm SIF. I am going to distribute a midterm SIF right as soon as the lecture is over, and I'm going to send it out. It's just like the regular SIF. I don't keep track of the email addresses, so your responses are private. And some of the feedback, I've asked some students about how they feel about the class, and some of the changes I've made to the course based on that feedback appear to be really popular. So I'm very grateful to the feedback. I want to make sure that I'm providing an outstanding experience for the class. I am going to open that, and then I will close it right before the exam, and I will not look at your responses until after I post your midterm grade. So it's going to be the same kind of simulation that you will do on the final. So last thing, if you go here, it has everything about the exam format. I have a suggested study schedule, so this can help you out. And then on Tuesday, you come in, you all destroy my midterm right there, you blow up the van. And then exam study questions. I have, so if you want to go like, okay, what's everything from Coding Challenge 4? I have a video for every problem that you've covered. The video has the solution, so you can use that as your own study guide. And so all the information you would want on the exam will be there. So there's 2 quick questions, and I will address them, and then I will dismiss. Okay, I'm sorry. How many questions are on the exam? As of right now, there are 30. I am making sure I might cut one out of the interest of fairness, that way that we have everything there. So are there any other exam-related questions? All right, on that note, go forth, study, and I expect you to dominate my exam on Tuesday. I'll see you all then.